All right, here we are deep into chapter 15 now. We've looked at some general property of carbohydrates. We've looked at some different structural projections, the Fisher projection, the Hayworth projection for monosaccharides. And so now we'll take a look into some other features of those monosaccharides. All right, so there you see in this particular fourth lecture, we're going to focus on the chemical properties of monosaccharides. All right, the first chemical property we'll look at is the oxidation of monosaccharides. Reducing sugars, that's a phrase you should get to know. It refers to monosaccharides with an aldehyde group that can be oxidized to a carboxylic acid. So we have these sugars undergo reaction with Benedict's reagent to give the corresponding carboxylic acid. If you remember, we talked about that Benedict's test for aldehydes back in the previous chapter. So that it involves mainly the copper 2+ going on to form copper 1+ as a Cu2O, a nice brick red from that deep blue solution. They're sugars that reduce other substances. That's why we call them reducing sugars. And they include the monosaccharides glucose, galactose, and fructose. And they're named by replacing the OSE ending with onic acid when they form the corresponding carboxylic acid. So for instance, glucose would become gluconic acid as a result of it being oxidized when it acts as a reducing sugar. Notice those three monosaccharides we name are our three most important monosaccharides. So these reducing sugars are pretty critical properties of monosaccharides. Okay, so let's look at the details of the oxidation of D-glucose, which is one of our reducing sugars. Again, not every sugar is a reducing sugar, but the ones that can undergo this oxidation are indeed reducing sugars. So we see the open chain form of D-glucose, which is not a very prevalent form, right? We said it's a trace amount less than 1%, but the fact that it exists means that we can have it available to undergo this oxidation. So in the presence of 2 moles of copper 2+ for every 1 mole of that open chain D-glucose, we have the rearrangement to form the oxidized form of glucose to form gluconic acid. In this case, since it was D-glucose, it's D-gluconic acid plus that copper 1 oxide, Cu2O, which is a solid suspension of that brick red. Very noticeable difference from that blue solution with the copper 2+ ions. Now, a couple slides ago when I mentioned fructose as one of our reducing sugars, it probably sent off alarms, bells, right? Because you know that fructose is a ketohexose. So we talked about those reducing sugars as having an aldehyde group that can be oxidized. And you know from your chapter on aldehydes and ketones that ketones don't get oxidized under normal conditions, especially gentle conditions like the Benedict's test. Well, guess what? Fructose, which is indeed a ketohexose, is also a reducing sugar because in the basic solution, like Benedict's, the carbonyl group can move from carbon 2 to carbon 1. So it can be oxidized just as glucose was. So we have that D-fructose, which is a ketohexose, having the carbonyl group on carbon 2. In the basic solution, like we have for a Benedict solution, we see a rearrangement of D-fructose to form D-glucose. So the carbonyl has migrated to carbon 1 to form an aldose from a ketose. And now that we have an aldose, well, of course, you just saw that D-glucose undergoes the oxidation. And since we've rearranged D-fructose into D-glucose, obviously it will do the same sort of chemistry. All right, so if we've talked about the oxidation of monosaccharides, it stands to reason we're also going to look at the possibility for reduction of monosaccharides. Just like we talked about the ability of aldehydes to be oxidized or reduced, look at the fact that these monosaccharides can also, depending on the particular monosaccharide, can either be oxidized or reduced or both. So monosaccharides can be reduced by converting that carbonyl group into an alcohol group. That produces a sugar alcohol, which is known as an additol from an aldose. And therefore, you see, we name those products by replacing the OSE ending, just like we replaced aldose with etol to get the alditols from the aldoses. So D-glucose reduces to D-glucatol But just like we've known glucose as dextrose instead of D-glucose, because glucose is so critical and such an important monosaccharide, it has another name, and a more common name actually, D-sorbitol. And so there we see the D-glucatol, or as it's more commonly known, D-sorbitol on the right, and it's a sugar alcohol. It has no carbonyl anymore. It has alcohols at both ends as well as every carbon in between. So hydroxyl groups on every single carbon, and if you read your labels, you'll often see those sugar substitutes for things like chocolates, sugar-free chocolates, even sugar-free popsicles. Sometimes we'll have D-sorbitol in the list. And so here, instead of calling it D-sorbitol, it's often just called sorbitol. And mannitol is another common one that you'll see as sweeteners in many of those sugar-free products, diet drinks, sugarless gum. Again, as I mentioned, popsicles, sugar-free chocolates. These will often be there, and they will give some people discomfort, gas, or diarrhea. Again, because the bacteria can often work on those, although the human body can't metabolize the sugar alcohols. Bacteria can, and even diabetics, you cannot get glucose to accumulate in the lens of the eye where it's converted to sorbitol, and that can cause cataracts to form. So it may not be a good solution for eliminating sugar, and actually a lot of diet drinks have moved away from it to the more popular things like Splenda instead of the sugar alcohols. So they're not as common anymore, but they were an early sugar substitute, and they still persist in a lot of things like the gum that we see here on our slide. Taking advantage of that feature we talked about earlier of the Benedict solution being able to reduce the copper ion from the Benedict solution from copper 2 plus to copper 1 plus and oxidize the glucose, we use that in one of the standard urine tests for diabetes. So a symptom of diabetes mellitus, which means sweet, that is a high level of glucose in the urine. The urine will actually taste sweet because the blood level exceeds about 160 milligrams of glucose per deciliter. Then the kidneys can't reabsorb it all. The glucose spills over into the urine, and the urine will have a sweet taste to it. Rather than tasting patients' urine, which is probably not a good idea because of other things that might be in there, or certainly not a pleasant sounding thing, even if it were entirely safe. Instead, we rely on these color tests, and the color of that test strip is a result of the amount of glucose in the urine, and therefore how much of it can be oxidized by the copper 2 plus in the Benedict's test. So you see there on the color strip, if you have low to moderate levels, it's green, and then high glucose levels will turn that Benedict's test to yellow or even brick red if it's really high. And so we see there the color strip being able to indicate glucose in the urine. All right, so before we leave this section of chapter 15, let's go ahead and have you take on this learning check. The task here is to write the products of the oxidation and also the reduction of D-mannose. So first oxidation and then reduction, and if you've already printed the slide, you could just do say oxidation on the right-hand side and reduction on the left-hand side of that D-mannose structure. So go ahead, pause the video here while you complete that task, and start it back up when you're ready to check your work. Good luck. Okay, and there we have it. If you noticed from the previous slide, we're dealing with an aldohexose, right? It's a 6-carbon sugar, and it is definitely an aldose because that carbonyl group is on carbon 1 with the carbon also attached to a hydrogen and then a carbon group, so it is definitely an aldehyde and therefore an aldose. So if we're going to reduce an aldehyde, we'll get a primary alcohol. So notice we changed that carbonyl group into a C single bond OH, so it's converted into an alcohol, and then another carbon hydrogen bond is added in there. If, on the other hand, we oxidize it, of course the aldehydes oxidize to carboxylic acid, so we put that instead of a CH bond, we have now a COH bond to form the carboxylic acid. So D-mannose was our starting substance. In the reduction, because we make a sugar alcohol, it's D-mannitol. In the oxidation process to the right, we make D-mannonic acid. So there we have it. Hopefully those are what you arrived at. You didn't have to write the names, but hopefully you're practicing already because you've gotten used to naming and you just love a challenge. So these were some interesting names, especially D-mannonic acid is quite an interesting name there. But as long as you could get the structures, you're in good shape. If you struggled with this one, please do try some other ones and then definitely reach out to me if it's still not making sense. Otherwise, we'll see you in the next lecture on Chapter 15.